Hi guys, thank you for joining me today. In this video, I will start a new module talking about bending stress. I would like to remind you what we covered so far. We covered that we have two types of stresses. The first one is called normal stress, and the second one is called shear stress. What we covered so far for the normal stress, we covered the case of axial stress. What you mean by axial stress? We have a member under the effect of axial compression or axial tension. If you remember that in the previous videos, if we have applied force F axially applied to the member, can be tension, can be compression. The normal stress equal this force divided by area. And in this case, this stress is called axial stress, but actually it's normal stress, perpendicular to the cross section. The indication or the induced stress will be perpendicular to the cross section. We covered also the shear stress due to the effect of torsion in the previous videos, previous module. If we have a shaft with a circular cross section under the effect of torque, we should expect torsion. We should expect the shear stress tau, maximum shear stress equal this torque time radius of this cross section C divided by J, the polar moment of inertia. And this stress is induced parallel to the cross section, like this. 0 at the center and the maximum at the circumference of the cross section. Keep in your mind, in this video, we have another form of the normal stress. It's called bending stress due to the effect of moment. If we have a member and this member under the effect of moment, this moment will cause normal stress, or to be more specific, bending stress. In the next module, we are going to cover another aspect of the shear stress due to shear force, capital V. That makes sense? So we are at this point right now. Under the effect of the applied moment, we will have bending stress. How much is this bending stress? It will equal the maximum bending stress equal this equation. Sigma, because it's normal stress, equal the applied moment M times C divided by I. In the general form, it will be sigma equal My divided by I. The stress caused by the bending moment, capital M, are called bending stress. They are normal stress, but they are due to the effect of moment, so it can be called bending stress. The bending stress in general can be M times Y divided by I. To calculate the maximum bending stress, I'm gonna multiply M times C divided by I. What you mean by M is the applied moment. I is the moment of inertia. If you go back to engineering mechanics, section properties, you will learn something about the section properties. Most of the time, it will be Ix, moment of inertia about x-axis. That makes sense? C is the distance from the neutral axis or from the centroid of the cross section to the extreme fibers. If we have this is your neutral axis, this is your centroid of the cross section. So the distance C will be measured from this centroid to the extreme fiber, the upper edge of the cross section or the lower edge, whatever the biggest. Y is a distance between the neutral axis or the centroid to the point you are looking for bending stress. If we are looking for a specific point, so the distance y is the distance between the centroid or the neutral axis to this point. We have a very important aspect of the bending stress. In the case of axial stress, the force can cause compressive stress. That's all. Or the force can cause tensile stress. That's all. But for bending stress, due to the effect of moment, this moment will cause tension in one side of the cross section and the compression on the other side of the cross section. So part of the cross section will be under tension. Another part of the cross section will be under compression, and your stress distribution looks like this. We have part under tensile stress, another part under compressive stress. How can I know which side of the cross section will be under tension and which side will be under compression? Look to the arrow. Look to the arrow of the moment. This arrow will have a tail and will have a head. The tension will be at the tail and the compression will be at the head. This point is very important. This point is very important and I would like to highlight it. Assume we have this member in 3D. And this member under the effect of this moment. We should understand this concept. So based on this arrow, this given arrow of the bending moment, I should expect tension at the tail of the arrow and compression on the side of the head of the arrow. So this side of the cross section will be under tension, and this side of the cross section will be under compression. This stress will be negative. This stress will be positive. Numerically, if we have the number line and we have sides of the number line with positive numbers, and we have another side of the number line with negative number, to move from negative to positive or to move from positive to negative, we have to pass through zero. That makes sense? So between the tensile stress at the bottom, at the tail of the arrow, and the compressive stress at the top, at the head of the arrow, we must have a line, which is called neutral axis. Neutral axis means it's not tensile stress, it's not compressive stress, it's not positive, it's not negative, it's neutral, zero. If you connect between this neutral axis and the stresses, if you connect between the neutral axis and the stresses, you can sketch the stress distribution. So the lower part of the cross section under the neutral axis will be under tensile stress. And this tensile stress is maximum at the extreme fiber at the bottom. And above the neutral axis, we will have compressive stress, and this compressive stress is 0 at the neutral axis and increasing to the maximum value at the extreme fiber at the top. This concept is very important. I would like to highlight it one more time in a different way. We are given this cross section in this member, and your bending moment looks like this. This is the given moment. Based on the arrow of the moment, we should expect tension at the top, at the tail of the arrow, and the compression at the head of the arrow. So I will have tension at the top of the cross section like this, and I will have compression at the bottom of the cross section like this. This stress will be positive because it's a tension. This stress will be negative because it's a compression. To move from tension to compression, or to move from compression to tension, we must go through something called the neutral axis. This neutral axis is a line in the cross section with no tensile stress, no compressive stress, so it's not positive, it's not negative. What does it mean? It's 0. And then I will connect between the maximum stress to the neutral axis, which is 0, and I will connect between the neutral axis and the maximum compressive tensile stress. So if you look to this stress distribution, 0 at the neutral axis and became bigger to be the maximum value at the extreme fiber at the bottom. And in between, we will have compressive stress. And between the neutral axis and the top, we will have tensile stress increasing to be the biggest value at the extreme fiber at the top. So how can I figure out the part of the cross section under tension or the part of the cross section under compression? I have to look to the arrow of the moment. Does that make sense? So at the arrow tail, we should expect tension. At the arrow head, we should expect compression. What is the value of the stress? If you are looking for value of stress at any point, I'm gonna use this expression. Sigma, the bending stress, equal the applied moment times the y distance divided by I. Y distance between the point and the neutral axis. If you are looking for this point, so this is y distance. If you are looking for the maximum stress at the top or the bottom of the cross section, I'm gonna use this expression. And the C represents also a distance, but distance between the neutral axis and the top. That makes sense? Or the distance between the neutral axis and the bottom, whatever you are looking for. If you are looking for maximum compressive stress, it will be at the top. Maximum tensile stress, it will be at the bottom. That makes sense? We have few examples covering this point. But before going through this example, I would like to remind you of something very important. If we have a rectangle with width B and the height H, and this rectangle has this the centroid, and this is your x-axis. We learned from engineering mechanics that we have something called Ix, which is called moment of inertia about x-axis. Ix will equal the parallel to xb time perpendicular to x h cube divided by 12. This is what we learned before. Also, we learned if we have a rectangle which is hollow rectangle, that means we have B1 outside rectangle, H1 for the outside rectangle, and we have B2 for the inside rectangle and H2. So we have, this is the material of the cross section. It's a hollow cross section. And the neutral axis or the x-axis is passing through the centroid. In this case, the moment of inertia I, x will equal the 1 for the outside rectangle minus the 1 for the inside rectangle. So P1 times H1 cube divided by 12 for the outside one minus B2 H2 cube divided by 12 for the inside rectangle. That makes sense? Also, we learned from engineering mechanics that if we have a rectangle and this is B and this is H, for some reason, the x-axis is here with a distance D from the centroid of this rectangle for some reason. In this case, the moment of inertia Ix will not be one value, but it will be two values added together. The first part, I'm gonna assume my x-axis is here. So BH cube divided by 12. But this is not the case. The assumed x-axis is moved by distance d to this position. So I have to add the area of this rectangle times the distance d square. Does that make sense? So this is the case if the x-axis of the cross-section is not passing through the centroid of this little rectangle. Why you are reminding us with this concept? Because sigma equal MC divided by I. Most of the time, this is IX because this moment is M about x-axis. Or MY divided by I. Most of the time, this is IX because this moment is MX. That makes sense? So let's go back to our example. We are given a cross-section. This cross-section given in 3 dimensions, but this cross-section looks like this. I section. The dimensions of this cross-section is 200 millimeter and 20 millimeter, 20 millimeter, and 260 millimeter. This one is not 300. 300 is the total height from the top to the bottom. But from this one to this one, you have to subtract 20 and 20. It will be 260. And the width of this web equal 20 millimeter. Does that make sense? First step to solve this kind of problem, the beam is subjected to a bending moment, M is given. We need to figure out the bending stress. And we are looking for the maximum bending stress. That means the equation I'm gonna use, bending stress sigma, which is maximum, will equal the applied moment times C divided by I. If you look to this equation, the applied moment is given. M is given. How much? 50 kilonewton meter. So what will be the value of the moment of inertia I? What will be the value of C, the distance C? So I will start with the part of section properties. This cross section will have a value of I, moment of inertia. And I'm looking for Ix because this moment is moment about x-axis, rotating about x-axis. Where the centroid of this cross-section will be located at the mid height. And at this position, I can put the x-axis. Then I can start to figure out the value of Ix will equal. This part of the cross-section is a rectangle. And the centroid of this little rectangle is here. So if you assume your x-axis for this little rectangle is here, so I can say parallel time perpendicular cube divided by 12. But I have to add another part, the area of this rectangle. Just to grab my calculator 1 second. The area of this rectangle is 200 times 20. It will be 4,000. This one moved from this position to this position. How much? It moved 130 plus 10 equal 140 square. This is the moment of inertia for this little rectangle. This is the point I covered here. If we have a rectangle and this rectangle has a centroid here and the x-axis is here, how can I figure out the moment of inertia for this part of the rectangle? So the first term, parallel time perpendicular cube divided by 12, BH cube divided by 12. I have to add the area of this rectangle times the distance between the centroid of this rectangle and the location of the x-axis. Area times depth square. This is what I did here. Since this rectangle is repeated one more time at the bottom with the same dimensions, with the same distance between the centroid and the x-axis, everything the same. So I can multiply this term by 2. Plus, we have this web. It's a rectangle. And the centroid of this rectangle at the same location of the x-axis. So I can say 20 times 260 cube divided by 12. That's it. Because this is the case that we have a rectangle and this rectangle has a centroid at the same location of the x-axis. So I can find out the moment of inertia. The moment of inertia will be 200 times 20 to power 3 divided by 12 plus 4,000 times 140 square times 2 plus 20 times 260 cube time or divided by 12. So the value will be 186360000. 186,360,000 millimeter to power 4. Does that make sense? Does that make sense? So far, so good. Since we are looking for the maximum bending stress, sigma maximum positive and the sigma maximum negative equal the applied moment 50 times C divided by I, 186,360,000. The same here. Keep in your mind, based on the given moment, this is the tail, so we will have tension at the bottom. This is the head, so we will have compression at the top. So your cross section will have tension at the bottom and the compression at the top. The maximum compressive stress will be at the extreme fiber at the top. So the distance C will be measured between the centroid of this cross section, the x-axis, the neutral axis, which is located at the centroid, and the top fiber. This is the value of C. How much is this value? It will be 150 millimeter. I think the distance C between the x-axis and the extreme fiber at the bottom will be also 150 millimeter. So if you would like to figure out the maximum tensile stress at the bottom, you have to multiply this moment by 150. This is the distance. This is the distance between the neutral axis or the x-axis or the centroid and the extreme fiber at the bottom. If you would like to figure out the maximum compressive stress, I will multiply also by distance C equal 150 between the neutral axis and the extreme fiber at the top. We have some adjustment before going forward because this 50 is kilonewton meter. So I can multiply it by 1,000 and another 1,000. Wow. Why? The first 1,000 to convert from kilonewton to newton. The second 1,000 to convert from meter to millimeter. So right now, the unit of the moment will be Newton millimeter. So this 50 will be multiplied by 1,000 times 1,000 one more time. So the final stress here will be positive. The final stress here will be negative. So 50 times 40.2 megapascal. 40.2 megapascal. Does that make sense? If you would like, but it's not required, we need only to determine the maximum bending stress. I determine the maximum bending stress at the bottom, the maximum bending stress at the top. They are equal because the distance C is the same. And one of them will be tension and one of them will be compression. If you would like to draw this stress, I can help you. So I will draw the stress on the cross section. At the bottom, we will have tensile stress. Maximum tensile stress, how much? 40.2 megapascal. At the bottom, I will have compressive stress. How much? 40.2 megapascal. At the centroid of this cross section, we will have neutral axis. This neutral axis is zero stress. So you can connect between the maximum stress and the neutral axis, and between the maximum stress here and the neutral axis. That makes sense? Okay. So I can draw my stress looks like this. Or we have a different scenario. You can represent your cross-section at this line and your neutral axis at the mid-height. This is the centroid neutral axis. I have maximum compressive stress at the top, 40, how much? 40.2 megapascal. I have maximum tensile stress at the bottom, 40.2 megapascal. And this stress is 0 at the neutral axis. So I can connect between the stress at the bottom and the stress at the top. This is the compressive stress, and this is the tensile stress. This is the best way to draw stress distribution. I'm gonna consider the cross-section as a vertical line. This is the top fiber of the cross-section, and this is the bottom fiber, and this point is the centroid. So I can put the stresses at the bottom, at the top, and the stresses at the neutral axis is 0. Then I can draw the normal stress distribution or bending stress distribution. We have another example. This example, we are giving a box cross-section. A box beam is constructed from 4 pieces of wood glued together as shown. If the moment acting on the cross-section is given, the value of the moment is given, looks like this. So looks like we have tension at the bottom and we will have compression at the top based on the given arrow. We are not looking for the maximum bending stress, but we have 2 points, point A and point B. So we are looking to figure out what are the bending stress values at this point. Since we are not looking for the maximum bending stress, we are looking for bending stress at certain points. I'm gonna use this expression, sigma equal the applied moment time distance y divided by y. Also, we have to start with the section properties. Here is the cross section. We have outside rectangle with dimensions 200 millimeter, width and the height equal 300 millimeter. This rectangle has another one inside because it's a hollow. The dimensions of the inside rectangle is 160 millimeter width and 250 millimeter height. So this is the material of the cross section. Keep in your mind, this cross section is symmetry. So the centroid will be located here, and here is the x-axis. I think this cross section looks like this case that I covered before. If you have 2 rectangles, one inside the second one, I can find out the moment of inertia using this expression. So the moment of inertia, I will start with the section properties. X will equal the outside rectangle 200 times 300 cube divided by 12 minus the inside rectangle 160 times 250 cube divided by 12. Then I can find out the moment of inertia of this cross section. 200 times 300 cube divided by 12 minus 160 times 250 cube divided by 12 will give you a value 2417 6666666.7 millimeter to power 4. That makes sense? If you would like to figure out the value of normal stress or bending stress at point A, you have to set up this equation. The applied moment is 10. The distance y between the neutral axis or the x-axis at the centroid and the point A. Your point A is located here. So the vertical distance between the neutral axis and this point, distance y, will equal 150 millimeter, divided by the moment of inertia. But we have some adjustment we have to follow. First of all, this stress will be negative. Why? Because this side of the cross section will be under compression based on the given arrow of the moment. Second, this one in millimeter to power 4. So this moment, I will convert it to Newton by multiplying it by 1000 and to millimeter by multiplying it by another 1000 to be Newton millimeter. So the final stress will be negative. How much? 6.2 megapascal, which is Newton per millimeter square. This is a bending stress at point A. For the bending stress at point B, I have also to use the same expression. The applied moment is 10. What is the vertical distance? Where is point B? Point B is located here. So what is the distance between the neutral axis and the point B? This distance, I think it will be 125 millimeter. So 125 millimeter divided by the moment of inertia. And this stress will be positive because it's on the side of the tensile stress based on the tail of the air. So the stress will be positive. How much? I forget to mention. This applied moment will be multiplied by 1000 to be in Newton times 1000 to be in millimeter. So the stress will be 5.2 megapascal. So the bending stress at the 2 points A will be compressive stress, negative 6.2 megapascal. The bending stress at point B will be tensile stress, positive 5.2 megapascal. We have another example. So we are given a beam, simply supported beam between two supports at A and B. We need to figure out the maximum bending stress, sigma maximum, in the beam, and we need to draw the stress distribution over the cross-section at the mid-span location. Mid-span location, this one. Mid-span. So we have two issues here. The first issue, what is the value of the moment? Do you know? So I have to start with the first part. What is the value of the moment at the mid-span? So I have to go back to engineering mechanics to figure this out. Just a reminder. We covered in engineering mechanics, if we have a beam between two supports, A and B. A is hinge, B is roller. And we are given uniform distributed load on this beam, 5 kilonewton per meter. First of all, at this hinge, I will have two reactions, XA, YA. At this roller, I will have only one reaction, YB. Then I need to apply the three equilibrium equations, summation f of x equals 0, summation f of y equals 0, summation moment at any point equals 0. Keep in your mind, this distributed load will be equivalent to 5 times 6 will be 30 kilonewton. If you apply these equilibrium equations, I can tell you XA will be 0, YA will be 15 kilonewton, and YB will be 15 kilonewton. Please go back to the engineering mechanics and see how to figure out the reactions or the review videos at the beginning of this course. Then I will do cut at the mid span. And I'm gonna use the left part. Actually, if you use the right part, that's fine. So here is the part you are working with, and here is your cut. Keep in your mind, in the left side, I will have this reaction 15 kilonewton, this reaction 0. I will have this part of the distributed load. And this distance will be 3 meters. And the value of the distributed load is 5 kilonewton per meter. This part of the distributed load can be equivalent to 5 times 3 will be 15 kilonewton. Keep in your mind, at your cut, we will have axial force, we will have shear force, we will have bending moment. I don't care about the axial force N, I don't care about the shear force V. My concern is the value of the moment. So I'm gonna take moment at the cut equals 0. I'm gonna assume counterclockwise is my positive. So N will be multiplied by 0 because I'm taking a moment at the same point, so we don't have distance. Shear will be multiplied by 0, and the moment does not need any distance because it's a moment. And we have 15 times distance 1.5 meter, and we have negative 15 at the reaction times 3, and this reaction is 0, equals 0. So the moment rotating counterclockwise will be 0. Any moment rotating clockwise will be negative. Any moment counterclockwise will be positive. Any moment clockwise will be negative. The only unknown in this equation is M, so I can figure out the value of M. This value will be 22.5 kilonewton meter positive. Positive means this direction of the moment, which looks like this, is correct. And this moment equal 22.5 kilonewton meter. Keep in your mind, in the previous two examples, the bending moment value is given. The bending moment value is given. But in this example, I used the engineering mechanics to figure out the bending moment value at the mid-span. Why the mid-span? Because the problem looking for the moment at the mid-span. Does that make sense? And based on your calculation, this value of the moment is positive. That means the direction you assumed is correct. So this arrow is correct. I have to put it as it is on the cross section. This is the first part of the problem, engineering mechanics part. The second part, which is the section properties. Just a moment. Section properties. We have this I section. The dimensions of this I section, 250, 250, and 20, 20, and 320. And this one is 20. Okay. Where is the centroid? The centroid is at the mid height because it's a symmetric cross section. I can put here the x-axis. And I can start to figure out the moment of inertia Ix. For this part, unfortunately, the centroid of this rectangle is here. So I can put the x-axis is here. So I will have the first part parallel 250 times 20 cube divided by 12. But we have a distance between the centroid of this part and the actual cross section as the actual x-axis. So this distance equal 160. So I have to add the area of this rectangle, which is 250 times 20. This is the area, 5,000. This is the area. Time the distance between the x-axis for this little rectangle and the x-axis for the whole cross-section, this distance is 160. So time 160 square. This is AD square. Since this rectangle is repeated one more time at the bottom, everything is the same, so I can multiply it by 2. Plus, for this rectangle, the centroid of this rectangle at the same location of the centroid of the cross-section. So I need only 2 multiply 20 times 300 cube divided by 12. That's it. So the moment of inertia will be 250 times 20 cube divided by 12 plus 5,000 times 160 square times 2 plus 20 times 300 cube divided by 12. The moment of inertia will be 301 33333.3 millimeter to power 4. We are ready. We have the bending moment value at the midspan. We have the moment of inertia, and we are looking for maximum bending stress. So sigma maximum equal M times C divided by R. Keep in your mind, if you are looking, your moment based on this direction looks like this. This is the moment. We have tension at the bottom. We have compression at the top. Keep in your mind, this distance between the neutral axis here and the top is C, equal 170. And the distance between the neutral axis and the bottom, C, equal 170 millimeter also. So if you are looking for sigma maximum at the top, which is negative, will equal the applied moment, 22.5, times C, 170, divided by I, 31,333,33.3, I can get the value of the moment, the value of the Bending stress, which is compressive stress. But keep in your mind, we have some adjustment because this moment kilonewton meter. So I will multiply it by 1000 to be in Newton, another 1000 to be in millimeter. So the stress will be negative. Okay. Just a moment. -12.7 megapascal or Newton per millimeter square. And the maximum bending stress at the bottom, which is tensile stress, will equal 22.5. I'm gonna multiply it by 1000 to be Newton, another 1000 to be in millimeter, time 170 to the bottom, divided by the moment of inertia. So the value will be the same, but both. If you would like to draw the normal stress distribution, which is required here, draw the normal stress distribution. I do recommend. Here is the cross section. I do recommend not to use the cross section, but I will project this cross section to be this line. I will project the x-axis to be this line. The stress, the maximum stress at the top, which is compressive stress, 12.7. So I will have here compressive stress, 12.7 megapascal. At the bottom, we have tensile stress. Here is the tensile stress, the arrow coming out from the cross section, 12.7 megapascal. At the x-axis, which is called neutral axis, at the centroid, we will have zero stress. It's not positive, it's not negative. Between 0 and the tensile stress, I'm gonna draw a line, and here is the tensile stress distribution on the lower part of the cross section. Between the 0 of the neutral axis and the maximum compressive stress at the top, I will draw a line, and then I will draw the arrows represent the compressive stress on the upper part of the cross section. This is called bending stress distribution on the cross section. That makes sense? And this is the problem in example number 3. For example number 4, we have a cross section which is a square. So we have square cross section 9 inch by 9 inch. And we need to determine the maximum, the absolute maximum. Absolute means I don't care it's positive or negative, it's a compressive or tensile stress, I don't care. In the beam. Unfortunately, the beam is given, but we don't have a specific location on the beam to use the moment. In the previous example, we are given a beam and we are given a specific position on the beam, which is the mid-span. So I figured out the moment at the mid-span. But in this example, we are not given a specific location or specific position. However, we are looking for maximum bending stress. Maximum bending stress will be at the maximum bending moment. So what is the maximum value of the bending moment? I don't know where. So this is the reason I will draw the bending moment distribution. I'm sorry, the bending moment diagram. If you need more information about how to draw the bending moment diagram, you can go back to the review videos in this course at the beginning of the course, or you can go back to engineering mechanics For me, we have fixed at A, so I will have three reactions, YA, XA, and MA. Keep in your mind, we have uniform distributed load here, so I will convert it to equivalent. How much? 800 times 8, it will be 6,400 pound. If you apply summation f of x equals 0, summation f of y equals 0, summation moment at any point equals 0, I can find out the reactions. This reaction will be 0. This reaction will be 7,600 pound. And this moment will be 4,800 pound foot. Probably the maximum moment will be at the fixed, probably, but I don't know. Make sure to draw your shear force diagram, because from the shear force diagram, I can draw the bending moment diagram. So let's try. I will go up by 7,600, move dotted because we have distributed load, go down by 6,400 until you reach to 1,200. Keep moving. So I will draw this solid line. One more time, if you need more information about how to draw the shear force diagram, bending moment diagram, you have two options. You can go back to the engineering mechanics course, or you can go back to the review videos at the beginning of this course. I will move constant until you have another concentrated load 1,200 to go down to 0. For bending moment diagram, we have a value of the moment here equal 44,800 pound foot. If you would like to figure out the value of the moment here, you have to use the previous value plus the area of shear force diagram in between. This value will be 9,600. And the value here will be 0. In between, I'm gonna draw a curve because we have distributed load. In between, I'm gonna draw a line because we don't have distributed. This is the bending moment diagram. The maximum value of the bending moment diagram is, so M maximum equal 44,800 pound foot, looks like this. This is the value of the moment MA. And this is the arrow direction. Looks like this. That makes sense? So I draw the bending moment diagram because I am not sure where is the maximum value of the moment. So if you look here, we have 0, we have 9,600, we have 44,800. So the maximum value is this one. Your cross section looks like this, square, 9 inch by 9 inch. So your bending moment diagram looks like this. So the moment of inertia I, which is very simple, it's just a rectangle, 9 times 9 cube divided by 12. So the value will be 9 times 9 cube divided by 12. It will be 546.75 inch to power 4. Once you have your maximum moment and your moment of inertia, I can say sigma maximum. One more time, here is your cross section. Here is the centroid, here is x-axis, this one is 9 inch, this one is 9 inch, and here is the bending moment M. So sigma maximum, if you are looking for, this one will be tension, this one will be compression. Keep in your mind, this distance C will equal 4.5 inch, this distance C will be 4.5 inch. So sigma maximum at the top, which is positive, equal the applied moment, 44,800. I'm gonna multiply it by 12 because it's in pound foot. If you multiply it by 12, it will be in pound inch. Time distance C 4.5 inch divided by the moment of inertia, which is very small, 546.75. Then you can find out your tensile stress. It will be in PSI. Sigma maximum at the bottom, which is compressive stress, equal the same moment, time 12 to be in pound inch, time distance 4.5 inch, divided by 546.75. You can get the negative value in PSI. If you would like to draw the stress distribution, here is the neutral axis. I will extend, or I will project the cross section to be this line. I will have this compressive stress. I will have this tensile stress. I will have this 0 at the neutral axis. Then this is the stress distribution on the cross section. But the problem asked for the absolute maximum bending stress, it will be this one or this one, both of them the same, regardless the positive or negative. That makes sense? So I would like to highlight a point. Sometimes the cross section is given and the bending moment is given. Sometimes the cross section is given, but the value of the moment is not given. So I need to figure out the value of the moment at specific point in the beam. So I need to use engineering mechanics. Sometimes the cross section is given, but where is the value of the moment on the beam? I don't know. So I draw the bending moment diagram and I look for the maximum bending moment value to give you the maximum bending stress.